Okay, good morning, ladies. This is Dr. Garais, your professor. This is MED110, also known as Anatomy and Physiology 1. It is Tuesday morning, week 2, January 12th, in the lovely year 2021. And just like we talked about last week, we're going to be talking about the precursor to disease, and we're going to be talking about a little bit basic chemistry today. So again, back to this this idea here that we talked about last week. Why is this so hard to? I just want to see the image. Let's just put it on a Microsoft Word so we can all see it. So we can have, it's good to have an overview of what and why we're looking at things. So the basic building block of who you are, and we're going to be talking about atoms and molecules today. Atoms make molecules, molecules then make cells, cells then make tissues, tissues, organs. Organs are, the different organs get lumped together into systems, and I don't know why they covered this poor man's penis, but makes an organism. Now, when we see the human being who's sick, right? Pathology, low G, study of disease, it didn't come out of nowhere. Somewhere along this line, normal, Al, pertaining to the rule, got violated or something went wrong. So, because if we look at how normal atoms and molecules, and somewhere in here is DNA. We'll be talking about DNA next week, and then cells next week as well, right? That's the basis of pathology and the basis of disease. People don't get sick out of nowhere. And if we understand how this pathway works, that's why when I was younger, I thought that's what pathology meant. Path to disease. But pathology means low G, study of a disease, but disease is a pathway, it's in a process, and it doesn't come out of nowhere. So what is our goal for today is, and if you look here, the thing that's due for next week, your tasks are for this particular course, you get to do these things right here in the bottom. Where is it? Here. Here's your task. And am I recording? Yes, good. Your task today is we're gonna go over basic chemical structures of an organism, human beings, macromolecules, bonding, and water. So we're gonna go through each one of these, and you are to submit a concept map. So I'm gonna put down a little video in announcements. I don't want to get into in greater detail on how to build a concept map. And your announcements are located, of course, in your main page here, where it says check announcements daily, right underneath the title. So I'll put it in here, and it'll be something like week 2, how to do a concept map. Because every week we do something called a concept map. So look one out. Find anything on Google. So this is what a concept map looks like. Doesn't necessarily have to be in color, but if you look at this, it's essentially you have a main idea, which today the main idea is chemistry, and then you have all these ideas. Now this one's color-coded. You don't have to color-code it, but you could see how we have a main idea will sprout other ideas, and the ideas are visual and they're connected. And that's what education is really. You're trying to connect all the pieces of the puzzle. And what are the pieces of our puzzle today? And if you look at any task and concept map, you could see we have objectives here, and they match the ones that are up here as well. So like if you're home playing along, right, you could hear and look up these videos. So we know we have to do bonds and bond strength, chemical reactions, inorganic compounds. Here are lovely, here are some notes here, right, regarding the basic chemistry, chemical bonds. And here as well is some more notes, and here as well are notes. So here, here, and here. And I remember one of them is a broken link. Nope, this one's good. This one's good. There's the broken link. This one's a broken link, but we have, let's look at here. In your lesson, so that's task 2. You're gonna have to make a concept map like what I just showed you. Discussion 2, of course. Thank you, Miss Archer. She already did hers, right? Discussion 2 is your typical 200 to, discussion 2 is 200 to 250 words minimum, right? And make sure you have your 7th edition APA format. And your lesson 2, look down here, right? And here's the same notes. Your lesson 2, of course, is due next week, is application assignment. You click on that, you download the case, and it's this PowerPoint, okay, which I'll be going over as well. And within the PowerPoint, let's see here, there are questions right here. Okay, I think 5 or 6 of them. And that's your lesson for lesson 2 that's due next week. You answer these questions that are embedded within the PowerPoint. And the discussion is about Alzheimer's. And if you look all the way at the very end, here's the Alzheimer's case study that they're talking about. Okay, so you're going to need this PowerPoint. And someone told me that it was a broken link, but as you can see here, it works fine, at least for my machine here. If you can't access it, give me a call, and what do you call that? And I will I'll email this thing directly to you, or heck, I'll even put it in announcements if enough people ask. So without further ado, let's get on with that PowerPoint. Why did I do that? Why did I minimize that PowerPoint? Because that PowerPoint is a nice starting off of what what bonds are. So bonds, if you watch the video, they're essentially what keeps us all together are atoms. Here's an example of a Bohr model, B-O-H-R. Niels Bohr was this guy who figured out how this all works. And an atom, which is the smallest building block of your body, is composed of, you have like a nucleus or a core, and that has a positive charged ion, which is called a proton, and a negative charged ion, which is called an electron. The electrons are the positively charged particle is in the middle, and these shells, which will represent energy levels, right? And the lowest energy level is this first ring, and then it gets a little higher, and then the last energy level is called your valence. Okay, now so an atom is comprised of proton, which is a positively charged particle that's in the middle, and neutron, which is neutral, that's also in the middle, and these shells of energy called electrons, and the electrons are negatively charged. So that thing about, if you ever watched the movie The Matrix, where what do you call that? What's his name? Morpheus says, you know, we're just batteries. In all intents and purposes, all living things are positive and negative. And this is actually through through these energy levels. That's exactly how batteries work, through the interaction of positive and negative charges, like electricity. Okay, so the valence electrons are the ones on the outside. Now, remember we talked about, let's go back to this one right here. This is Na. If you can recall, that's the symbol, or that's the chemical abbreviation for sodium, right? If you remember your medical terminology, if you have hypernatremia, that means you have too much salt. Hyponatremia, you have too little salt. So if you look here, sodium is what they call an ion, and ions are charged particles. If you look at here, the electron here is 2 in the first shell, electron shell, so that's complete. On the next one, it's 8. Okay. On this last one, you could see that there's only 1 electron. It's actually short 1 electron. So since it's short 1 electron, that means the balance would be towards the positive. So that's why Na is written Na with a little plus sign. So that makes it an ion. And ions, we're going to see in a moment, they're highly reactive. That's why if you put sodium in water, it should explode, just sodium. But if you put sodium and you combine it with chlorine, that forms sodium chloride. And then that brings us to this next topic of bonds. So if we're looking at something like this, right, you could see how it goes, if it goes, what something is in a neutral state. If something's in a neutral state, like argon, you'll see how the first shell, 2, and then the next shell is all even, 2, 4, 6, 8. If you look at here, fluorine, it's short 1. Lithium, it's short, right? Oxygen, 1, 2, 3, 4, 5, 6. It's short 2. That's why it actually has 2 negatives. So fluorine, lithium, and oxygen, these are highly reactive things. Maybe if you know a little bit about liquid oxygen, that's what we use as fuel. It's highly reactive. Lithium is highly reactive. We use lithium in pharmacology for bipolar patients because it's highly reactive with the chemistry. But if you look at argon, this one, it's even, right? So if it's even, that means it's in its neutral. It's as neutral as it's going to get. Okay? So remember that word even, or homeostasis. That's what our body likes to be. It doesn't like to be excitable, but it gets excitable when it has to be in order for it to do something. Okay, so now you got your answer to question 1, assuming all of the following atoms are in a neutral state, which atom is most likely to be chemically inert? The one that's most even, the one that doesn't have anything extra on the outside, like this one here, electron, and these electrons here. That's why oxygen is highly reactive. Okay. So I just mentioned the ionic bond. Ionic bond, ions are, if we recall, the sodium has 1 less electron. Okay, therefore it is positive. Now chlorine has an extra electron. That's why it's a negative. So if you ever look at the chemical abbreviation of a sodium ion, it'll have Na with a little plus sign. And chlorine will have Cl with a little minus sign. That means it's an ion, and that means it's highly reactive. You put sodium in water, it'll blow up. Chlorine, I believe it should react and turn into its gas state pretty darn quick. So you put them together, they're both ions, sodium plus, chlorine negative. You put them together, and you have an ionic bond. It is the first bond. Now, what are bonds? Bonds are relationships with the valence electrons of atoms, and they attract towards one another, a plus and a minus. They attract towards one another, and they form a link. Okay, an ionic bond. So if you see one ion with another ion, right, that will lead sodium chloride. So here's an example of what it looks like in chemistry. You have an Na plus, and then of course I add it with a chlorine as negative, and that will give me or yield sodium chloride. Now, you might see things like this in chemistry all the time. You have an H plus a Cl minus. That's a plus 1 with a negative 1. That will yield. How do I make an arrow here? There we go. Hydrochloric acid. So these are examples of hydrogen bonds. Sodium chloride, and sodium chloride, of course, is table salt. HCl is hydrochloric acid. Okay, and these are examples of sodium ionic bonds. Okay. Now, we're going to talk also about how they also react with water, because remember, that's one of our goals for today. So what is likely to happen to the electrons when a potassium bonds to a chlorine, right? Since this question was right after the ionic bond example, and let's look at the example that we had here. I don't want to give away the answer, but potassium is plus 1, and I want to add it to a Cl minus. So it's going to yield just like the HCl, potassium chloride. Oh, by the way, table salt is sodium chloride. Now, this answers the question, didn't you guys ever wonder why you don't just fall apart when you jump into water? It used to bother me when I was a kid. Like, if I threw my sandwich into the water, it would fall apart and would start to disintegrate, especially the bread. But why is it when I'm swimming all day, I don't simply fall apart? And that's that's what human beings and all living things are. We simply don't fall apart because we have these connections, we have these relationships, these bonds that keep us all together. Okay, and these bonds require, and we know about with the valence, they require energy. Okay, so look at the little explanation here on ionic bonds, and then you could pretty much figure out what goes on, right? Now, let's get to the next bond. They have this nice little skit that they have here. I just like get right to the nitty gritty. This is hydrogen gas. Okay, so H plus with H plus. This is a hydrogen gas here is a nonpolar covalent bond. Nonpolar meaning it's sharing its electrons and it's sharing it evenly. There's no pole, there's no, the poles, like North Pole, South Pole. There's no one side. And covalent, co means what? Together. Valence is your outer electron shell. So hydrogen gas, right? Even O2 or oxygen, right? This is hydrogen gas H2. That's nonpolar covalent. That's an example of nonpolar covalent. Okay. So you can look up here, which are the following. This looks like a beautiful question on one of my exams, right? We already know that sodium chloride is an ionic bond. So that already will eliminate which one of these is an example of a nonpolar covalent. Because remember, this is your what do you call it? This is answering these questions is your lesson that's due for next week. So now, what's a polar covalent? Remember we mentioned hydrochloric acid, right? Which is you have a hydrogen ion and a chlorine ion sharing. Well, a more specific, another way to also characterize that kind of bond, hydrochloric acid, is polar covalent. Now, how do we know that it goes if I ask about a polar covalent bond in an exam? If you see these, this is a delta, means partial positive charge, partial negative charge. So HCl is an example of a polar covalent bond in this particular case. Another great example of a polar covalent bond is water, and we're going to show how water also has a partially positive and partial negative. So the difference between a nonpolar covalent bond and a polar covalent bond, nonpolar, right, they share equally. But if you see here in a polar covalent bond, they share unequally, and which causes a partial positive and a partial negative charge. All right, and we could see here which of the following molecules is polar covalent. We already know sodium chloride is out because that's ionic, but we could see here there's some potential. NAF kind of looks like NaCl, so we can, that's also ionic, so I can kind of eliminate B and D. So now you got to decide, is it C or A? That, and you could look up the chemical structure, and if you see it, partial negative, partial positive, then it is a polar covalent. Here's water, H2O. H2O has 2 hydrogens and 1 oxygen. The oxygen is now emitting a partial negative and a partial positive. Now, the interesting thing about water is because of its partial positivity and partial negativity that it creates, it also creates hydrogen bonds. So the attraction of this hydrogen, partial positive to a partial negative, that is a hydrogen bond. Okay, and the hydrogen bond is relatively weak compared to these other bonds that we talked about because the hydrogen bond needs to be flexible. And that's what water is, it's flexible. And the neat thing about water is since it has a partial positive and partial negative charge, it can pull ionic bonds apart. So for example, I have sodium chloride. We already know that sodium chloride, sodium is positive, we recall here. Chloride is negative, right? We know that table salt, sodium chloride, right, is solid, but if I throw it in water, what will happen? The partial positive will start pulling it away at the negative, which is the chlorine. The partial negative will start pulling away at the positive, which is the sodium, and it'll pull it apart. And if it pulls it apart, what happens? The salt looks like it disappears, but you drink that water, it didn't disappear. It's there in solution. And that's one of the wonderful properties of water, which we'll discuss. So now you got the 4 bonds. Let's see if there's any more bonds that we have to talk about. And again, here's another question that you need to answer regarding your lesson 2 for next, lesson 2 for next week. So the 4 bonds that we just talked about are ionic, nonpolar covalent, polar covalent, and hydrogen bonds. And we gave examples of each. Don't you think I could have an exam that does this? Right? Like question 6. So start preempting me for future quizzes and future exams, especially your midterm. And that's a better way to study. Ask yourself what's important. And right now we spent a good 20 minutes just on bonds. So you know that the bonds have to come out. You know that there are 4 types. You know you have some examples. Don't you think I could easily just take this copy and paste it and put that just like this on an exam? Sure. Hey, don't you think I could just, since you guys will be doing the homework, I could just take this, mix it all around and ask which one's ionic, which one's nonpolar covalent, which one's polar covalent, which one will form a hydrogen bond. Okay. Okay, and looks like how many, let's see, of course, there's another question. So there's like 8 questions. I said there was like, what, 6? I think they're 10. Number 10 is easy. How many electrons in a valence for this particular, this is sulfur. And remember, valence is the last electron shell. It's the one that most likely will react to whatever it's bumping into. So, you know, you could just do the math, right? It's the one on the end. And you could answer that here. Okay. And lovely, here is the different types of bonds and some example. And there's another, and of course, last but not least, this is your discussion case. Your discussion will allude to an Alzheimer's case, and it is in this PowerPoint at the very, very end. All righty. So let me put this PowerPoint aside, and then let's look at our objectives, because we always got to go back and look to see, are we on plan? Are we on task? So, and this video, out of all these videos, this one's a nice one on the different types of chemical bonds, and they have actually the same examples. So we now know that we went through now chemical bonds. You now know what an atom is, because an atom is comprised of a proton, a neutron, and shells of electrons. Because of the different number of protons, neutrons, and electrons, those are the different elements. The different elements connect to each other through different kinds of bonds, and the different kinds of bonds have different kinds of bond strength. We already mentioned that hydrogen ion will be like one of the weakest ones. And in here, there's a nice little chart in this video that talks about its strength. Now, let's talk about chemical reactions. And in order to talk about that, this one, the note, this link isn't good, but this one right here, let's click on that. Okay. Now, we just mentioned that chemistry is all about how these atoms and molecules and these electrons and protons and neutrons all interact with each other. All of this requires energy. It's the reason why you have to be, we as a living thing has to be always breathing and always eating, okay? We eat because we don't necessarily, like, for example, I don't know, I skip breakfast, but if I had breakfast, I know I should, it's the most important meal of the day. But if I had breakfast, it would have a whole bunch of things in it. And we're going to talk about the organic compounds in a moment. But it's not really the Egg McMuffin that my body wants. It wants to break down the items of the Egg McMuffin, which is the bread made out of carbohydrates, the cheese, which is made out of fat, and whatever protein is then bacon or whatnot. Great, I'm making myself hungry. And all of that, your body wants to take that, and those are the reactants, and they want to make a product. And the two products that your body consumes and requires, and just like the energy that we were talking about, in order to maintain life, right? So if you stop breathing and stop eating, your body will cease to take these reactants to make them products. This is called metabolism. Meta means change, bol means growth. So that's all your body is trying to do, is take these reactants, the Egg McMuffin, right? Or sausage McMuffin with cheese, and then convert it to the products. And the two basic products that the human body loves is oxygen and glucose. and glucose is your basic 6-carbon sugar. Okay, so that's why dietitians are so hard on us, and a lot of physicians and DNPs and whoever's taking care of us is so hard on us, because we're the only species on the planet that eats for fun, that eats because we're sad, that eats just because it's 10 a.m. Right? Every other thing eats just to survive, and eats just enough to survive. But we're the only animal that eats way beyond what we require. And every time we eat, it requires energy. Now, there's these things called enzymes. Enzymes are proteins, and they catabolize things. Catalyzation, or this word catalyze, if you see here, it means it speeds things up. Now, you could look at your body like this. Without an enzyme, it takes forever to get up this hill of energy. This hill right here is called your activation energy. So without an enzyme, your body can't break down things to get to the products. For example, if you take that Egg McMuffin sandwich or whatever, you put it outside, it'll take what? Weeks to months before it gets broken down into the products that we need. But if I eat it, I chew it, and it goes in my stomach, and hydrochloric acid breaks down things, and I have enzymes. If I have an enzyme, it goes through this path. And we can all agree that this path right here, that's an easier path to drive your car up. It takes less energy. It's lower. Just imagine you on your bicycle trying to get up this long, long hill. But once you get up there, it'll just fly right down to products. And this is how chemical formulas and chemical reactions work in your body. It requires enzymes. And what do the enzymes do? It lowers the activation energy, and so that we require less energy, we're more efficient, and then we can get to our products. And the two main products in organic chemistry, and organic meaning us as human beings, living things, right? Sodium chloride is not a living thing, but us, we're a living thing. And we're going to talk about organic compounds in a moment, because it requires enzymes. Now, chemical reactions that break down carbohydrates, proteins, and fats. If you look here at this sentence here. Now, remember that sausage McMuffin with cheese? The carbohydrate is the bread. The sausage patty is protein. And of course, the cheese is the fat. You need all three. And you need enzymes to break down each one. So the enzyme that breaks down carbohydrates, let's write this down. Right? If I want to break down a carbohydrate, the enzyme that'll break down a carbohydrate is called, oh, great. Now it's bothering me. Let me do the easy ones first. Proteinase breaks down proteins. Lipase breaks down fats, also known as lipids. And amylase breaks down carbohydrates. So if you notice on all three of them, it has a suffix ASE. Okay. That connotes that this chemical that we're talking about is an enzyme. And again, the function of the enzyme is to lower the activation energy so we can get from reactants, the thing that we ate, to the actual products that we need, right? Which is, our glucose and our oxygen. Okay? Now, if you'll also notice the little quick note that I made here, it's specific. Proteinase breaks down specifically proteins. Lipase will break down specifically lipids. Oh, by the way, these enzymes, so if you have a ASE, that equal enzyme, these things also have coenzymes that help it even lower the activation energy lower. By the way, these things are called vitamins. And the best way to get it is your diet. Your body likes to break down things. It likes to have a diet. It likes to go through this process. That's why just eating pills all day is not the answer. And you can't starve yourself either. And also, any diet that removes any one of these things to this little formula here, right, is not a good idea because your body needs all three. But the best thing regarding most diets is portion control, because remember, like I just said, we're the only animal species on the planet that eats beyond its fill, eats beyond what it needs, and I am living proof of that. Now you could see that how this enzyme and the substrate. So the enzyme for lipid is lipase. So it only will break down lipids, and that's the substrate, okay? And then it's chemically specific, like a lock and key. And then it forms an enzyme substrate complex, and then it's changed. And that's what happens with this carbohydrate, protein, and fat. The reactants then go through this with aid of the enzyme, and then the end product is what? Glucose and oxygen. Question? Anyone have a question? No, we're good. Let me real quick. Whoever Sanchik is, could you kindly put in the chat your full name so I can
Yes.
I can take down your attendance. Everybody else, let me write real quick.
How do I change that?
You could go here if you want, or just tell me right now. What's your go?
Okay. Sona Sut.
Oh, Miss Soot, I remember you.
Yes, thank you. I'm having a hard time with this
That's
Zoom
all right.
thing.
It's a process. You get used to it. All right.
Nice meeting you.
All right. I'm gonna put you back on mute. And again, anyone has any questions, kindly put it in the chat, and then or also wait until at the end of the lecture so we can we can answer your questions. So coenzymes, cofactors, those are all vitamins, but again, just taking pills, not a good thing. Now, if you see here enzymes and substrates, don't you think we could block them? Right? Because that's a chemical. What if I had a chemical that looks kind of like this and it gets in the way? I could block them. So there are certain things in your body that your body would like to block at times, and there's certain things in your body that it wants to activate. So that's also another theme in anatomy and physiology where things get turned on and turned off. And this is one way we can do it. And actually, this enzyme model or this lock and key model, we'll see again when we're talking about hormones. And we'll also see again if you take my pharmacology course or whatever pharmacology course. This is essentially how drugs work. Didn't you ever wonder why when you have a headache, you take Tylenol? Like, how does the Tylenol know where to go where the pain is? Well, it knows where to go because the Tylenol is going to fit right in a space that is like a lock and key, like a puzzle. How does your body know when to release insulin, when to release glucagon? How does it know when to release dopamine or epinephrine or any of the chemicals? Because sometimes the chemicals are floating around, and if it sees an open lock, the key will open it. Or you could block a key. Have you ever had someone put gum in your lock or in your locker at school? That's one way we could do it. So there could be also inhibitor molecules. You could also block. So let's say, for example, the product is, let's say, a chemical that's making me depressed. So what could I do here? If I gave you a drug or a reactant that will block the product, then, that's one way to do it. And isn't that what medications do? Some medications block things. Some medications enhance things. Now, regarding a question for an exam, we already know it goes, what is an enzyme substrate complex? It's when the reactant or substrate binds with the enzyme, and it binds it, and it has a fit. it looks like it fits chemically. And you can see in this drawing here. Hydrochloric acid, pepsin. No, now this part here in the middle, you could read that later when we're in the gastrointestinal anatomy and physiology. This starts going into other things. Oh, look at this. Here's more enzymes. Amylase breaks down starch or carbohydrates. Trypsin, which breaks down, is another type of a proteinase, which break down polypeptides, right? And lipase, of course, breaks down lipids, right? That's why when I do a test on you, I look at your triglycerides and your fatty acids. Because if you've been like me throughout this whole quarantine, eating nothing but Doritos and beer, right? What's going to happen? Your body's going to break down these lipids and you're going to have these products. You're going to have triglycerides and you're going to have fatty acids. And we can look at that in your blood. Okay. So let's now look at this next part of the notes. All right. All these other parts here, you could skip. The 4 groups of biological macromolecules. Now, the other chemistry that we were talking about, you know, sodium, chloride, hydrogen, water, well, not water, but those are minerals and elements that are inorganic. They're in the ground. You know, these elements that we can find, like salt, chlorine, you know, that's in the ground. Argon, fluorine, that's all in the ground. But here, carbohydrates, proteins, lipids, and nucleic acids, that's organic chemistry. That's organic macromolecules. These things are in living things, living tissues. That means us. So what are carbohydrates? As the formula suggests, it's what? A carbon and water. Because if you hydrate yourself, that's water. So you see here, it's CH2O, right? And carbohydrates are broken down into several types. You have monosaccharides, disaccharides, oligosaccharides, and polysaccharides. What does it mean? Mono, the prefix means 1. So 1 is a very simple number. So monosaccharides are your basic sugars. And the biggest one that we need to be concerned of in human beings is glucose. Okay? Glucose is a 6-carbon sugar. It is the main fuel or the main product of us eating. Now, fructose is fruit sugar. Then you have ribose and deoxyribose, which forms our DNA, and RNA, which is important in genetics. We'll go over that next week. Okay, so that's a monosaccharide. It's a simple sugar. Disaccharides are a combination of sugars. So you take a monosaccharide, you put 2 of them together, and what do you get? You get things like sucrose, maltose, and lactose. And lactose, we know regarding lactose intolerance, that is the milk sugar. And if you notice, all the sugars, they have a suffix OSE. So glucose, fructose, ribose, deoxyribose, maltose, lactose have OSE. Oligosaccharides are a little bit more, 3 to 9 monosaccharides. And polysaccharides, known as complex carbohydrates, this is the stuff that easily turns to fat. And the biggest one is starch, right? So polysaccharides, something that has a lot of sugars all together. And classic example, you know, like potatoes, you know, Asian white rice, you know, the white sticky rice. Ugh, that's vicious. That's heavy in starch. The thing about starch is it tastes so good. But the problem is it gets converted to fat very, very easily. So that is carbohydrates. Now, there are diets like Atkins that want to eliminate carbohydrates, but if you look at the new Atkins 2 and the Atkins 2 modified, they decrease carbohydrates. You can't get rid of carbohydrates. You need them. But you can do what? Decrease your intake. Same thing. There are some diets that eliminate proteins. That's not a good idea. You need proteins. And what's a protein? A protein is a carbon, hydrogen, oxygen, and nitrogen. That's why its abbreviation is CHON, or CHON, and that's a protein. Proteins are little, they're caused by these little beads or these little like Legos of amino acid building blocks that are connected to a peptide bond. So proteinase breaks down those peptide bonds and then breaks it down to amino acids. So all a protein is a bunch of chain of amino acids. And it's made out of carbon, hydrogen, oxygen, and nitrogen. And the carbohydrate is made out of carbon, hydrogen, and oxygen. Lipids, they're made out of carbon, hydrogen, oxygen. We already talked a little bit about fatty acids, triglycerides, steroids, waxes. There are things in your body that need fat, okay? And lipids is the important part of lipids or fat is that it stores energy. It stores carbon, hydrogen, and oxygen, things like glucose, right? Which are made out of carbon, hydrogen, and oxygen for when we need it, especially if we're in a starvation state. Okay. Lastly, nucleic acids. That is the fourth category of organic compound. That's DNA and RNA. The DNA, or deoxyribonucleic acid, is the blueprint of who you are. It's the code of everything, even your behavior, how you act, what color your eyes, are you going to be tall, are you going to be short, actually has the code of when and how you are to die. Right? If we can, we've over the last 5 decades, we've been trying to, we already know how to map out the DNA, but trying to understand how it turns on and off things. For example, how it turns on and off disease, how it turns on and off cancers. When we're talking about genetics, that's the thing that medical science really wants to know. But because of media, and we all know what the media can do, both positive and negative, right? Everyone thinks that all we want to do is clone people. No, we want to actually figure out how disease gets turned on and off. And RNA, ribonucleic acid, is the messenger. It's kind of like a liaison, a go-between between the blueprint of who you are, the DNA, and to your rest of your cell, which creates all the 3 other things that we talked about: carbohydrates, proteins, and fats, also known as lipids. Okay, so as a side note, oh no, if we still had lab, probably would mess with this, but other than that, use this as notes, and these notes are located here. Chemical and physical digestion background of proteins, fats, and carbohydrates, that's right here. So right now, we went through some chemical bonds. We also went through some macromolecules. That's the proteins, fats, and carbohydrates. We already went through some bonding, okay? And let's now talk about water, which is this part here. So we click on this. Remember, this link here is broken. So don't click on it and go, hey, Dr. Garais, it doesn't work. Of course it doesn't. It's broken. But there's other sources of that material for here and here, okay? And also you have that PowerPoint as well. So let's go here, student guide for water. Why is water so special? Now, oh, here's lovely, lovely notes here for ionic bonds, covalent bonds. You could look that up, look through there, but we want to get to this part here. Solubility. We already talked about water being partial positive and partial negative. We also talked about how water, if I take table salt, which is a solid, and I put that into water, it will break apart that salt, that table salt, into its separate ions, sodium and chlorine, right? And the sodium will go in the will be attracted towards the partial negative charge of water, and chlorine, which will be attracted to the partial positive, okay? Because remember, opposites attract. And then it will pull it out, and it can pull it out into solution. Now, what are these things? Suspension, colloid, and a solution. Now, a suspension is all of these things are mixtures. And a suspension, that's when, when you mix something and you could still see uh, um, like chunks in it, right? And that's why some medications you have to shake. Like a good example of like a suspension is orange juice with the pulp in it. Okay, that's one way to look at it, because if you leave it standing, right, the pulp ends up at the bottom of the your glass, or especially if it's freshly squeezed orange juice. Now, what's a colloid? Colloid, right? In a suspension, it can the parts can fall out, but in a colloid, you know what? I think I'm not. Suspension versus suspension colloid solution. Let's. I'm not explaining it right. Let's just look at an actual example. Here you go. When you're looking at a mixture of things, right? A mixture of something is like the best way to look at it is like Kool-Aid. Everyone knows Kool-Aid, yes? So Kool-Aid is made out of powder, which is the dry parts, and water, which is the wet part, right? Let's keep it simple like that. Okay? So what's a solution, right? A solution is called homogeneous. You can't easily separate out the Kool-Aid and the Kool-Aid powder and the water. So if you look here, it's all one thing. So when you drink Kool-Aid, it's all one thing. But I guess a suspension is when like that pulp I told you about. Let's say, for example, I put way too much Kool-Aid in it, right? There's going to be powder floating around, right? But in a suspension, if I let it hang out, the little the little extra bits by gravity is going to start to fall in the bottom, and that's called a precipitate or precipitation. Okay. Now, in a colloid, a good example of a colloid is like a mixture like mayonnaise. It's all mixed up, but it's like hung in suspension. It's like suspended up in there. Okay. So here's some examples, right? What's a common example of a suspension? Like muddy water, flour and water. You can see that there's particles floating around in there. My example of a suspension is mayonnaise, because mayonnaise is mixed up of oil and egg whites and some other things, right? And and it'll be all floating around there. So solution, think homogeneous. Suspension and colloid, think heterogeneous, all floating around. Now the suspension, if you leave it alone, will cause a precipitate, but a colloid will be all, it'll stay in suspension. It'll stay all floating around like that. I think that's a better way to look at it. Now, why are we mentioning that? We're mentioning this because there's different kinds of solubility. Solubility is the ability of the powder part of your Kool-Aid, and the powder part is called your solute, and the water part is called your solvent, right? So here you go. So the larger portion of it, which is like the water part, is the solvent. There you go. And the powder part of your Kool-Aid is solute, and the solvent for an aqueous solution is water, but the solvent could also be like could be oil, it could be alcohol. But for aqueous solutions, which is us human beings, since we're made out of more than 66% of water, we are in an aqueous solution. And we mentioned saturated If it's too much, right, like if I put way too much powder, right, you know that the powder will start settling at the bottom, because remember, there's only so many water molecules that have partial negative and partial positive slots available to pick up, salt or any powder. Sometimes solutions are hydrophilic, which we'll be talking about next week when we talk about the parts of the cell. There are certain parts of our body, it loves water, hydrophilic, and there's certain parts of our body, hydrophobic. It's water fearing. It pushes away water. Did you ever wonder how all your organs can keep everything separated? Well, because of solutions, things could be in solution in fat. Things could be solution in water. Things could be hydrophilic, which love water, or like fat, things could be hydrophobic. If you put vegetable oil and and water together, they'll separate because oil is hydrophobic. Okay. And again, here is that model again of our water. And you could see here the partial positive hydrogen, which will attract negative particles, and the partial negative of oxygen in water, right? Remember, water is H2O, 2 hydrogens and 1 oxygen. Okay. Now, another neat thing that this partial negative and partial positive does has surface tension. This is actually, we'll be talking about this. This surface tension is required in our lungs when we try to exchange oxygen and carbon dioxide. So this is real. This cohesion or surface tension is really, really important in our lungs. And there's a chemical called surfactant that's really important in neonatology or newborns. Here's another example of how hydrogen bonds get formed in water, and these hydrogen bonds cause this adhesion that we're talking about, this surface tension that we're talking about. Heat capacity, nice to know, but these other items here are a little bit more important. So solutions, partial positivity, partial negativity, formation of hydrogen bonds, the definition of hydrophilic versus hydrophobic. These things are more important than knowing the specific heat of water and the boiling properties of water. You'll learn that when you're in if ever, for those of you who are going into nursing, you will be most likely taking SCI 260, which is biochemistry. So let's look at our goals. Did we meet them? Did we look at basic chemical structure of organisms? Yes, we did. Did we look at the macromolecules? Yes, right here in these notes right here. Did we look at bonds? Yep, all these videos and the PowerPoint. And did we look at water? Right here in these new notes here, student guide to water. So now you'll have enough to create this concept map. And I'll put, I think I'll find a video on YouTube and I'll put it right in announcements on how to do a concept map. Okay, so let's recap. Okay, and that's it's like a crash course in basic chemistry. So what's due next week? This task. So that's task 2, concept map, and you could put it on a Microsoft Word document or preferably a Microsoft Word document. And if you want to know how to do that, I can, like for example, this is a Microsoft Word document. I can, here you say draw, you can draw it, using that, or insert, you can put shapes. Let's say I want a circle here, and let's call this lecture 2, chemistry. And then what are my 4 things? Basic structure of chemical organisms, right? So I can then insert shapes again, arrow here, and I have my different arrows to my different topics. And then one topic could be, to put here, one topic could be bonds, and then you put, you could put other arrows here. Now, another thing you could also do for those of you who aren't as computer savvy, but if you're not computer savvy, isn't that something that you gotta go work on? But if you're in a crunch, what can you do? You can take a ruler and maybe some coins, and just be very neat about it, and then take a picture of it on your phone, and you could submit it that way. But learning how to do this on Microsoft Word, um, that's a better. You really should learn how to do this kind of thing, because if you look at the way your memory works, it works like a map. And that's what this is. It's a concept map. Your concept should always start in the middle and then fan out towards the different things like chemical structures, bonds, macromolecules, and water. And then each one of those has different concepts. And you could make it as basic, and eventually it's going to look something like this. Well, maybe not as complex, but here was the example that we had. You have your main topic, and then here, branching outward, are the subtopics. So you have one set of topics here, another set of topics here, another set of topics here, kind of like wheels, spokes on a wheel, just coming out. Okay, so that's what's due next week. I'll try to put up. I'll not try. I will put up a video. We don't like that word "try" in healthcare. We do. I will put up a video for it in your announcements. And of course, what else is due next week? Your discussion 2. And if you look at discussion 2, it'd say, based on the completion of the case study, and that's the last PowerPoint slide on that PowerPoint, complete the application question on Alzheimer's disease. Let's look at that real quick. So if I look at the practical application, using your textbook and other resources, research the topic of Alzheimer's disease. And in 200 to 250 words with a 7th edition APA formatted citation from either a .org, .gov, or .edu, describe how the different types of chemical bonds relate to Alzheimer's disease and the mechanism of action on how drugs. So you have 2 things you have to answer. What do chemical bonds have to do with Alzheimer's disease? And how do we use drugs to try to treat disease? By the way, there is no treatment for Alzheimer's. It's progressive. We only can slow it down. The drug of choice is donepezil. It's good for 4 to 6 months. It helps slows it down so that the patient can, get all their stuff in order, right? Because Alzheimer's disease, there's no cure. It's degenerative. That means it gets worse and worse and worse. Its main sign and symptom is dementia. The patient progressively starts losing their memory, and then little by little, they start losing everything else, okay? And it's because of these beta amyloid plaques. So in your discussion, you have to define what is a beta amyloid plaque. What does that have to do with chemical bonds? And what do drugs like donepezil do to these beta amyloid plaques and do for Alzheimer's disease? And that's your last, right here, slide 45 in your PowerPoint that's located in your lesson 2. So you have discussion 2 due, your task 2 due next week, and the lesson 2, of course, in that PowerPoint, answer the chemistry questions. And it states there's 10 or 11 questions. So if you look at your PowerPoint, you look to see inside the PowerPoint, it's like CQ, yeah, there's 10 questions. CQ10, CQ9, CQ8, and that's all inside the PowerPoint. So one way you could do it is you copy and paste all those questions and your answers to a Microsoft Word document. Make sure you put your name on the document. That's another thing, another pet peeve I have. Gang, learn how to use this. Let's say I'm I want to submit this concept map. Somewhere put your name, right? Put what class is this for? And what task, lesson, or whatever. So this will be like task 2, right? What is this called again? Chemistry concept map. Okay. And of course, when you save it, oopsies, up here. When you save it, all right, do the same thing. So I know what it is. A lot of people just put homework. I don't know what that is, because, and also it could get lost in the shuffle. And also that's also a great way, if you do it like this, if you lose a file and then you try to search it again, you can find it again and quite easily. And of course, me, I like dating things because let's say, for example, I have a different version of it, you know. So, you know, do something like this somewhere in the file name or somewhere on the page, so I know it's you. Because many times the only reason how I know it's you is because you submitted it. But get used to labeling it, because then you're going to get to the point where you know, if you're organized, you can find things a lot easier. All right, let's take attendance one last time to see if 1, 2, 3, 4. There's 5 people on this call. I guess there are 4 other people who don't want a job. So congratulations for being here. You get full credit, of course. And for those of you who are watching at home and who didn't attend, I cannot award attendance. Give me a call so we can look at some sort of makeup. At this point, I'm going to